Welcome to G Fun Facts Online. Today we are turning our gaze toward the deepest, oldest shadows of the cosmos, where the James Webb Space Telescope has uncovered something that, frankly, should NT exist. We are talking about the mystery of the little red dots, a discovery that is currently breaking the standard model of how our universe began. To understand the gravity of this situation, we first need to look at the story of cosmic evolution as we understood it for decades. It was a comfortable, logical timeline. The story went that vast clouds of neutral hydrogen collapsed to form the first stars. These stars clustered together into small, messy, infant galaxies. Deep within the hearts of these galaxies, black holes eventually formed and began to grow, feeding on gas and dust. In this traditional view, the galaxy came first. The monster in the middle grew up alongside it. It was a symbiotic relationship, governed by what we call the Magorrian Relation. In the local universe, the distinct rule is that a central supermassive black hole is always the junior partner, typically comprising about 0.1% of the galaxy's total mass. If you weighed the galaxy, you could predict the size of the black hole with remarkable accuracy. That was the rule. Then came the James Webb Space Telescope, or JWST. Within its first year of operations, JWST targeted an epoch known as the Cosmic Dawn, less than a billion years after the Big Bang. Astronomers expected to see faint, ragged clumps of infant stars, the chaotic precursors to modern galaxies. Instead, the telescope found hundreds of bright, compact, crimson spheres. At first, these were dismissed as data quirks, or standard galaxies shrouded in dust. But as the spectral data began to trickle in, a startling realization took hold. These were not normal galaxies. They were tiny point source objects, emitting light with an intensity that defied physical models. They were nicknamed Little Red Dots, or LRDs, and they have since become the center of the biggest controversy in modern astrophysics. The paradox they present is chilling. These dots appear to host supermassive black holes that are far too big and far too early. Some seem to be almost as massive as the galaxies they inhabit, completely upending the 0.1% rule, and suggesting that in the infant universe, the monsters might have formed before the cradles. To really grasp why this is keeping astrophysicists awake at night, we need to dissect the anatomy of the mystery. When JWST analyzes the light from these objects, it sees a contradictory signature known as a V-shaped spectral energy distribution. Imagine looking at a graph of light intensity. On the blue side, in ultraviolet and visible wavelengths, there is a faint bluish glow. This is the signature of a small, young host galaxy, a cluster of baby stars unpolluted by heavy metals, shining clearly. But then, as you move to the near-infrared part of the spectrum, the line shoots upward violently. The light becomes incredibly intense and deep red. This isn't the redness of old, dying stars. It is the redness of attenuation, meaning light that has been processed through thick layers of dust and gas, or light that has been stretched by extreme cosmological redshift. This red excess is originating from a point source, a singular region of space smaller than a few light years across. When astronomers broke this light down using spectroscopy, looking for the fingerprints of elements, they found the smoking gun. They found broad-line emission, specifically broad hydrogen alpha lines. In astrophysics, broad lines are the signature of speed. They indicate gas swirling at thousands of kilometers per second. There is only one engine in the universe capable of whipping gas around at those speeds within such a confined space, and that is the accretion disk of a supermassive black hole. But here lies the problem. To produce the luminosity observed in these little red dots, the black holes powering them would need to be millions, perhaps billions of times the mass of the Sun. And they are existing at a time just 600 to 800 million years after the Big Bang. The universe was barely out of its infancy. As one researcher involved in the Cosmos Web survey put it, it is like walking into a nursery and finding a toddler who is 7 feet tall and weighs 300 pounds. It simply does not fit our understanding of how things grow. This brings us to the impossible ratio, the overmassive paradox. In the modern universe, the black hole is a tiny fraction of the galaxy, but in these little red dots, the black hole appears to be 10%, 50%, or even nearly 100% of the host galaxy's stellar mass. This is not a relationship, it is a dominance. It suggests that these black holes did not grow inside galaxies. It implies they might have formed first, acting as gravitational anchors around which the galaxy later coalesced. This forces cosmologists to confront two uncomfortable questions. First, how did they get so big so fast? Standard accretion, or eating gas, has a speed limit known as the Eddington limit. If a black hole eats too fast, the radiation pressure blows the food away. To reach these masses in just 600 million years, these black holes would have to break the speed limit of the universe continuously since the moment of the Big Bang. The second question is, where are the X-rays? Active galactic nuclei, or eating black holes, are famous for screaming in high-energy X-rays. Yet, when astronomers pointed our best X-ray telescope Chandra at these little red dots, they saw nothing. The dots are X-ray silent. So we are looking at a monster that is too big to exist, eating faster than physics allows, and hiding in a cloak of silence. As the community scrambled to explain this, the debate split into three leading theories. The first and currently most popular hypothesis is the superdusty baby quasar, also known as the Cocoon Theory. This model suggests that we are looking at a unique phase of black hole evolution that effectively no longer exists in the modern universe. In this scenario, the black hole is indeed there, but it is not as massive as the raw luminosity suggests. Instead, it is cocooned in an incredibly dense sphere of gas and dust. This cocoon solves two problems at once. First, it blocks the X-rays completely, explaining the silence. Second, it reprocesses the high-energy radiation from the black hole into the infrared red light we see. Crucially, recent simulations suggest that the broad lines used to weigh these black holes might be deceptive. Typically, broad lines mean high gravity and thus high mass. But in the LRDs, the gas might not just be orbiting. It might be part of a massive dust-driven outflow, a wind blowing outward. If we mistake this wind speed for orbital speed, we vastly overestimate the mass of the black hole. A groundbreaking 2025 study, led by researchers at the University of Manchester and the Max Planck Institute, suggests that once you correct for this cocoon effect, the black holes shrink. They are still massive, perhaps 100,000 solar masses, but they are no longer impossible. They are merely heavy seeds, growing vigorously in a dust shell. However, even if they are smaller than we thought, they are still huge for their age. This leads to the second theory, the heavy seed scenario. If the black holes are not optical illusions, we must rewrite the history of seed formation. Standard theory says black holes start as light seeds, the remnants of the first stars, weighing perhaps 10 to 100 solar masses. Growing from 100 to a billion solar masses in a few hundred million years is mathematically difficult. The little red dots offer the strongest evidence yet for heavy seeds or direct collapse black holes. In this scenario, vast clouds of pristine gas in the early universe did not fragment into stars. Instead, kept hot by background radiation, they collapsed monolithically, directly into a black hole weighing 10,000 to 100,000 solar masses in a single day. If LRDs are these heavy seeds, the paradox of too big, too fast vanishes. They did not need to grow fast because they were born big. Then there is the third option, the exotic imposters known as supermassive stars. A minority of astronomers propose an even wilder alternative. What if there is no black hole at all? Some models of the early universe allow for the formation of supermassive stars, titans weighing 10,000 to 100,000 times the mass of the Sun. These stars would be so luminous they would burn through their fuel in a cosmic blink of an eye. Their spectral signature, a cool red photosphere with broad emission lines from stellar winds, could look suspiciously like an obscured black hole. If LRDs are actually supermassive stars, they would be the missing link of stellar evolution, the precursors that eventually collapse to form the heavy seed black holes we just discussed. Regardless of which theory wins, we seem to be converging on a new understanding of cosmic evolution, which we can call the gray hole solution. Standard quasars are blue, standard galaxies are white or yellow, dusty galaxies are red. But little red dots are distinct because they are point source red. The Cocoon model posits that the LRDs are a transition phase. Phase 1 sees a heavy seed black hole form in a dense gas cloud. Phase 2 is the LRD phase, where the black hole eats voraciously, buried in food. The density of the gas is so high that light essentially bounces around inside the cloud, shifting to red, before escaping. Finally, in Phase 3, the black hole grows large enough that its feedback winds and jets blow the cocoon away, revealing the visible, blue quasar we see in the slightly older universe. This timeline implies that JWST has captured a specific biological stage of the universe, the metamorphosis of black holes. We are seeing them in the womb. The existence of little red dots forces a revision of the galaxy first model. If these objects are indeed overmassive relative to their hosts, it suggests that black hole first evolution is real. In the pockets of the early universe, gravity collapsed gas into black holes before it collapsed gas into stars. These black holes then acted as the seeds for galaxy formation, their gravity pulling in the dark matter and gas that would eventually birth the Milky Way and its cousins. It implies that the universe was a far more violent top-down place than we imagined. It wasn't a slow buildup of structure. It was an era of monsters, born from the dark, shaping the cosmos by brute force. So, what is the road ahead? The mystery of the little red dots is far from solved. The cocoon hypothesis is currently the most attractive, because it saves our understanding of physics by not requiring us to break the Eddington limit, but it requires proof. That proof will come from two sources. First, longer exposure spectroscopy. JWST needs to stare at these dots longer to detect faint lines of oxygen and neon, which can distinguish between a black hole's accretion disk and a supermassive star's surface. Second, variability. Black holes flicker as they eat. Stars generally do not flicker on short timescales. If LRDs flicker over the course of months or years, the supermassive star theory dies, and the black hole theory wins. Until then, these little red dots remain the most provocative objects in the sky. They are red warning lights on the dashboard of our cosmology, signaling that the early universe was stranger, denser, and more monstrous than we ever dared to dream. The paradox of the overmassive black hole is not just a statistical anomaly. It is a glimpse into the dark, violent birth of the galaxies we call home. Thank you for listening to this deep dive on G Fun Facts Online.